To all viewers and subscribers, good morning to all of us, especially to those commenters who have commented uh, nicely. And I don't know what I don't believe those things that they are telling, but I appreciate it very much. Good morning and thank you very much. Now we start considering the stress-strain relationship. Before we try to consider the stress-strain relationship, the properties of the materials, let us have this stress-strain diagram. Now, from this diagram, we can see some important points wherein they are terms which will be used further in considering the design of machine elements. Of course, being a relationship between stress and strain, the stress we have taken that is equal to the force divided by the area, and the strain is equal to the deformation over the length, which is symbolized by Greek letter epsilon, the delta over the length. Now, having the stress-strain diagram, we have here the curve that is produced if we are going to test a certain material. Now, in testing this material, we will be able to have some corresponding significant points, which these significant points will have the result in trying to test the material. This is a general concept with respect to the curve produced by any material under testing. So the first point that we will be able to have is what we call the proportional degree. Meaning to say that proportional, that is the point. Beyond that proportional limit, is the stress and the strain proportional with each other. As the strain also is by definition, is the mass below which strain is proportional to the stress, as I have stated. Now, the next point that we have is what for the elastic limit. The elastic limit, by definition, that is the limit beyond which the material will start to deform and will return to its original shape when unloaded. Next to that, of course, is what we call the yield point or the yield strength. That is the yield strength is the strength for a specified deviation from the proportional limit. So meaning to say that yield strength is the strength or the basis for designing machine members or machine elements. And next to that, of course, is another basis used as used for design of machine members or machine elements, which is the ultimate strength. Ultimate strength is the maximum strength to which a material can will stand. That is the ultimate strength. Of course, after that is already the rupture, meaning rupture is the strength at failure. So that is now the point at strength at failure. Then the strain by the definition is deformation, either in terms of elongation or in terms of shortening per unit length. That is depending on the type of flow that a certain material will be subjected to. If the material is subjected to a tensile stress, the deformation that will happen will be in terms of elongation. Or if the force acting on the material is compressive in nature, there will be a deformation in terms of shortening or in terms of contraction, which the equation, of course, we will have for strain will be equal to the deformation divided by that. Now, we have here some important properties of a certain material, which we have to take into consideration. These properties must be taken into consideration because they are considerations that we have when we try to design machine members or machine elements. First one is the preparedness. But the first property in here is the preparedness, which that is the tendency to fracture without appreciative deformation. So that is a property that that will fracture without appreciative deformation, meaning it will no longer be considering the yield strength. It is the ultimate strength that will be considered for a brittle material. That is the brittleness. Next is the ductility. Ductility is the property that permits permanent deformation before fracture. So that is a property of a material that the material will deform permanently, meaning to say it can no longer return to its original position or original shape. That is deformation before fracture. Next is elasticity. Elasticity is the ability of a material to be deformed and return to its original shape. So that is a property of the material that when a certain material is subjected to a certain force and and when deformed, it can still return to its original shape because of that elastic property. Next is the hardness. Hardness is simply the resistance to indentation. Then next is machinability. Machinability by definition is the relative ease with which a material can be cut. That is the machine, machinability property. Then next is malleability. By definition, malleability is susceptibility to extreme deformation. Plasticity, by definition, the ability to deform considerably without the then stiffness. Stiffness is the ability of the material to resist deformation. And last property that we consider here is toughness. Toughness is the ability to withstand shock load without breaking. So those are the important properties of the material that we are going to take into consideration. Then strain and elongation, the relationship that we are going to have for the strain and elongation. Forces, one consideration that we have to take is that forces acting on the body forces change in each shape, which are proportional to the magnitude of the force. These changes are called deformation or strain. Now, the relationship of the strain and modulus of elasticity. The stress we have taken that is equal to F over A. And the strain is equal to the formation divided by the depth. And the modulus of elasticity is stress over the strain, which if we are going to substitute that, S is equal to F over A, and strain is equal to over L. And if we are going to consider the equation formula by cross multiplication, considering the deformation, that will be equal to the force multiplied by the length all over the cross-sectional area multiplied by the modulus of elasticity. Or that is deformation is equal to FL over AE. Then of course we have here, that is the Greek letter L is the representative, and F is the force, L is the length, A is the cross-sectional area, and E is the modulus of elasticity. Now, after considering deformation due to stress, we now consider thermal stresses, that is deformation due to thermal. We have to understand that any material expands when its temperature is elevated and contracts when its temperature is lower. If the material is restrained from expanding or contracting, stresses are, or we can also consider thermal stresses on a peak due to changing temperature. This change causes the bar to contract or expand. If the bar is restrained, the expansion or contraction causes internal stresses. That is thermal deformation or increase of thermal expansion multiplied by the quantity T minus T sub 4. Equating thermal elongation with elongation due to stress. That is, deformation is equal to F over 80. Therefore, we can consider deformation that is of thermal expansion multiplied by quantity T minus T sub 4. Plus equal to F over where F over K equals F over F over T by cross multiplication. Therefore, stress, thermal stress now is equal Definition of thermal expansion multiplied by velocity multiplied by velocity minus theta rho, where the formation here is the case of for strain in terms of thickness or strain that is the condition of thermal expansion meter per meter per degrees centigrade or per degree Fahrenheit. L is the length in terms of the meter, S therefore is axial stress, Newton per square meter. T is the final temperature in terms of degrees centigrade or degrees Fahrenheit. T sub O is initial temperature in degrees centigrade or degrees Fahrenheit. Now, what we have considered, have taken from the elongation due to pressure or elongation due to depth, we now apply it on some problem. The first problem is as a contacted block are stress of 25,000 psi. I is equal to 10 times 10 psi. So we are get block that is 25,000 pounds per and module of 10 or the solution will have that is the formation is equal to Fn over 80. We have taken the S is therefore we can do that equal Fn over substituting values. The formation now is equal to 25,000 pounds per square. That is multiplied by 100 is all over 10 pound per square and now my pound per square remaining unit in that unit. So that formation will now equal 0.25 over 8. So the next problem we will consider is for the formation to so that we understand what is the density of it by 4 interest by 12 experience and increase temperature from no stress temperature. From no stress temperature or the 8 degrees Fahrenheit heat temperature where we are creating of thermal expansion at 6.9 times 10 degrees Fahrenheit. And what so we are given this here. One half and the coefficient of thermal expansion and the mode of deformation equation taken from stress and the thermal deformation which is equal to V to be able to fight for whatever is. So we have taken available that we have here the data that uh, 1/2 inch by 4 inches by 12 inches by bar. The change in temperature that is from an initial 0 to 80 degrees Fahrenheit, both is Fahrenheit. The conditions of thermal expansion is 6.5 and 10 right. And is 3 times 10 to the 7. Now, the relationship that we are going to consider is the stress deformation in terms of the stress and the deformation in terms of the thermal stress. So we can equate the two, which we will have it in here, which of course the relationship that is for the strain being deformation divided by L. From this relationship in here, we have taken that the deformation is equal to coefficient of thermal expansion multiplied by the length multiplied by the change in temperature, or that will reduce to strain is equal to coefficient of thermal expansion multiplied by the change in temperature. Now, from the stress proportional to strain, where S is equal to modulus of elasticity multiplied by the strain, therefore, stress now is equal to modulus of elasticity multiplied by the coefficient of thermal expansion multiplied by the change in temperature. So that we can have this stress equal now to the modulus of elasticity 3 times 10 to the 7 pounds per inch squared multiplied by the coefficient of friction 6.5 times 10 to the negative 6 per degree Fahrenheit multiplied by 80 degrees Fahrenheit. So Fahrenheit and Fahrenheit cancel out. So the remaining unit in terms of the pounds per inch squared, where we have the stress at 1.56 times 10 to the 4 pounds per inch squared. Then from the equation F is equal to SA. To be able to find for the force. The F now is equal to SA, which is now equal to S is 1.56 times 10 to the 4 pound per inch squared. Cross-sectional area of the tie rod, 1/2 inch by 4 inches. So that our tensile load will be equal to 31,200 pounds. That is shortening, a compressing. So we have here that is from F is equal to SA. That will be equal to 1.56 times 10 to the 4 pounds per inch squared multiplied by 1/2 inch multiplied by 4 inches, or that will give us 31,000 pounds force, which, as stated, this is a tensile load. But the deformation will be in terms of shortening because there is a decrease in temperature, which, as stated before, for thermal expansion, there is a decrease in temperature. The thermal deformation will be in terms of contraction or shortening. That is why we can have the tensile force. Although this is a tensile force, it will be a shortening because of the decrease in temperature. Now, a while ago, we have taken into consideration problems involving this deformation due to simple stress. Now we have here two problems actually involving thermal deformation. So these are two problems which involve thermal deformation. The first problem we have here, as stated, the steel rails on a railroad track are laid when the temperature is 40 degrees Fahrenheit. The rails are welded together and held in place by the ties so that no expansion is possible due to temperature change. What will be the stress in the rails when heated by the sun to 120 degrees Fahrenheit, considering that the uh, coefficient of thermal expansion is 0.000007 per inch per degrees Fahrenheit per inch, or simply per degrees Fahrenheit. And E is 30 million PSI. So we are given here that is 0.00007 per degree Fahrenheit for coefficient of thermal expansion. Our initial temperature is 40 degrees Fahrenheit and the final temperature is 120 degrees Fahrenheit. Modulus of elasticity is 30 million PSI. So the deformation due to increase in temperature is taken from, that is, deformation is equal to the coefficient of thermal expansion multiplied by the length multiplied by the change in temperature, considering that as equation number 1. And the deformation due to simple stress, which is now equal to deformation is equal to FL over AE, where, of course, we have taken that S is equal to F over A. So this term F over A here becomes simply S multiplied by L divided by E. Consider that as equation 2. Now, if we equate equation 1 and 2, which equation 1 in terms of deformation is equal to coefficient of thermal expansion multiplied by the length multiplied by the change in temperature, equal now to SL over E. L and L cancels out, therefore S. By cross multiplication, that will be equal to modulus of elasticity multiplied by the coefficient of thermal expansion multiplied by the change in temperature. So that will be equal to 30 times 10 to the 6 pounds per inch squared multiplied by 7 times 10 to the negative 6 multiplied by 120 minus 40, or the stress now is equal to 16,800 pounds per inch squared. That is the stress developed in the rail when heated by the sun to 120 degrees Fahrenheit. So we have here another problem. That is, as is stated, a railroad track is laid at a temperature of 10 degrees Fahrenheit with gaps of 0.01 feet between the ends of the rails. The rails are 30 feet long. If they are prevented from buckling, what stress will result from a temperature of 110 degrees Fahrenheit? Coefficient of thermal expansion equal to 6.5 times 10 to the negative 6 per degrees Fahrenheit. So the gap between the rail is 0.01 feet. So 0.01 feet meaning that half of 0.01 feet would be the expansion of the first rail, and half of 0.01 feet will be the expansion of the next rail. But of course, if this is having a half 0.01 feet expansion, there is also a 0.01 feet, half of 0.01 feet expansion here. So that each rail will have a total expansion of 0.01 feet. So therefore, we have here the given data, T1 equal to 10 degrees Fahrenheit, T3 that will be 110 degrees Fahrenheit, a gap of 0.01 or deformation for each rail of 0.01 feet. The length is 33 feet. We are asked to find for T sub 2 and if the stress develops. So solving for the deformation of thermal deformation, that is equal to deformation is equal to coefficient of thermal expansion, the length, the change in temperature. Initial to find for the T sub 2, that is temperature when they meet, when the two rails meet. So that is equal to 0.01 feet equal to 6.5 times 10 to the negative 6 multiplied by the length 33 feet multiplied by the change in temperature T sub 2 minus 10 degrees. Or T sub 2 now will be equal to 2.145 times 10 to the negative 3 plus 0.01 divided by 2.145 times 10 to the negative 4. T sub 2 will be 56.62 degrees Fahrenheit. And solving for the stress now is equal to coefficient of thermal expansion multiplied by the modulus of elasticity multiplied by the quantity final temperature minus the initial temperature, which T sub 2 now becomes the initial temperature when stress is induced or developed. That is to prevent buckling or deformation. So the stress induced or developed is equal to 6.5 times 10 to the negative 6 by 30 times 10 to the 6 pounds per inch squared. This is the modulus of elasticity for steel multiplied by 110 minus 56.62, or the tensile stress induced or developed is equal to 10,409.1 pounds per inch squared.